right, now for the second half of the problem, we're asked to find the velocity after 100 meters of the fall. So what we're going to do is we're going to write out our equation, summation of forces in the y direction is equal to ma. And in this case, acceleration is not quite zero yet because the forces are yet to be canceled out, the gravitational and the drag force. So the diver is still gaining some speed, therefore the acceleration is still not zero. So for this case, we could write out the equation to be ma equals, which is the force in the y direction, equals the constant times velocity squared, which is our drag force, minus our gravitational force mg. Now, we could write this a in a different form, which is, could write it this way, dv dt. And all this is saying, it's saying that the change of velocity with respect to time is equal to acceleration, dv dt. And we could also go a little further with this and say that dv over dy times dy over dt is equal to our second half of the equation. And notice that nothing is changing here. I didn't add any expressions. It's still, if I cancel out the dy's, I would end up with dv dt, and that is just equal to acceleration. Now, what we could do is we could reduce this term, dy dt, because this is all it's saying is that the change in position over time. This is what this is saying. So, well, that's just velocity, right? Because dy is in meters and dt is in seconds, so that's meters over seconds. That's just v. So we could do this and say m dv over dt times the velocity is equal to our drag force minus the gravitational force. Now, let's separate and, I'm sorry, this is y. And let's put the like terms together. So let's take this dv to the other side and the v to the other side and leave the dy on the other side. We will get, if we do that, we'll get dy is equal to, well, this is going to flip because dv is on top. To get dv over here, this is going to go in the denominator, and this part is going to stay as m dot v. Okay, so now we're going to add an integral to both sides, and we're going to try and integrate this to get a expression that reflects position in it, because all we're trying to do here is add y to this equation, which is a position variable, because we can't put any we can't put the 100 meters in any term over here, so we're gonna have to do some differential equations here, right? So now if we differentiate, well, we're gonna have to write this in a different way. This is gonna go from y naught to y dy, and this is gonna go from 0 to v. And the reason this is 0 because when the skydiver is in the plane, he's stationary. and he's not moving, so his velocity is 0. So we're going to start on a new piece of paper over here, and if we go ahead and integrate, we got v on top and v squared on the bottom, so we could just use u substitution here. U is equal to k v squared minus mg. Therefore, our du is equal to 2k v, and this term would go 0 dv. And if we go ahead and solve for du, for v dv, I'm sorry, we would get 1 over 2k du equals v dv, which is this term over here. Actually here, the m is a constant, we could take this one out. So let's do that. Let's take the m out, and this is a constant. 2k is a constant as well, so we could take that outside the integration. So we would be left with y naught to y dy is equal to the, well, m over 2k integral from 0 to v all over 1 du over u. And the integral of 1 over u is just the natural log of u. And the integral of 1 is just y. 1 dy is just y. So we would get, on the left side of the equation, we'd get y from y naught to y is equal to m over 2k of the natural log. I'm going to substitute back the u, which we had it as k v squared minus mg from 0 to v. Okay, we're done with this one. Okay. So now what we could do is we could substitute our values over here. We'd get, on the left side, we'd get y minus y naught. And if we substitute 0 into this equation, we wouldn't really get 0. We'd get the natural log of negative mg, because this term would go 0, but this term is still there. So we'd get m over 2k natural log kv squared, let's put this in brackets, minus mg minus the natural log of k 0 minus mg. And we know that the relationship between two natural logs subtracting is just whatever inside the parentheses would divide in the other side. So we'd get something like this. Natural log v squared minus mg all over negative mg. This is equal to y minus y naught. Okay. So now all we gotta do is solve for velocity over here. So I'm gonna go ahead and take the mass divided by 2 times the constant to the other side, and we're gonna get 2k y minus y naught divided by m equals the natural log and now we need to cancel out the natural log, so that's we're going to multiply by an exponential on both sides, and we get exponential of 2k y minus y sub naught divided by m. And we're going to have to multiply by negative mg and add an mg over here to the other side. So that would be and if we divide by k and take the square root, we'd get that the velocity is equal to mg minus mg times exponential that's not a negative, it's just a typo, divided by m all divided by constant k over square root. Now if you want to simplify it even further, if you want to plot this or graph it, you could take out the mg, and that would just be you would have -1 plus the exponential, or you could multiply by even -1. You would have 1 minus the exponential. Keep it simple. And now if we plug in our values, we get m is 70. Can't put the units here, I'd run out of space. And gravity is 9.81 meters per second squared. Again, exponential 2k 0 minus 100 divided by m, which is 70, over 2k, which is 0.25. And if you plug this into your calculator, you should get, let's see, 38.8 meters per second. And that's the velocity after 100 meters of fall. And that's it.